All right, let's dive into a tale of two chemical families. They're hydrocarbons, the building blocks of everything from the fuel in your car to the plastics all around us. They look almost identical, but they behave in completely different ways. So what's the deal? Why is one so stable and the other so reactive? Well, the entire secret, as we're about to find out, is hidden in the bond.
You look at this, and it seems so simple, right? A single line connecting two carbons versus a double line. But I'm telling you, that one tiny difference on paper is a massive deal. It changes literally everything about how these molecules behave.
So that brings us to the big question. Why is one family of hydrocarbons so, boring and unreactive, while the other is just ready and waiting for a chemical reaction to happen? It all comes down to the shape, the geometry, and the energy locked inside those bonds.
Okay, so let's get a proper introduction to the two main characters in our story. First up, we have the saturated alkanes, and then we have their much more exciting cousins, the unsaturated alkenes.
So what's the difference? Well, on the left, you've got the alkanes. They only have single bonds between their carbon atoms, and they're called saturated because they are jam-packed with as many hydrogen atoms as they can possibly hold. Think of a sponge that's completely full. Now on the right, you've got the alkenes. Their defining feature is that carbon-carbon double bond. That double bond means they're unsaturated. They haven't maxed out on atoms yet. There's still room to add more.
Let's start with our first family, the alkanes. We're going to figure out exactly what makes them so stable, so chemically reserved.
And it all starts with this blueprint, a concept called hybridization. Think of it like this. A carbon atom has a few different types of building blocks, called orbitals. For an alkane, the carbon atom takes one s orbital and three p orbitals and mashes them together. That process is called sp3 hybridization, and it creates four identical, super strong places to form single bonds.
And what do you get from that sp3 mixing? You get this perfect, three-dimensional pyramid shape called a tetrahedron. All the bonds are pushed as far apart as possible at 109.5 degrees. These strong single bonds, known as sigma bonds, form a really stable, protected framework. There's just no easy way for another molecule to attack it, which is why alkanes are pretty unreactive.
In chemistry, the functional group is basically the interesting, reactive part of a molecule. It's the point of attack. But because alkanes are so stable, with all their bonds tucked away neatly, they don't really have one. There's no obvious weak spot, no chink in the armor. So if alkanes are like these little chemical fortresses with no obvious way in, how on earth do you get them to react? Well, you have to use brute force. We're talking about a massive amount of energy.
And their reactions are pretty dramatic. You've got combustion, which is really just a nice way of saying you set them on fire. Then there's cracking, where you use insane heat and pressure to literally smash big alkanes into smaller, more useful pieces. And then there's this one, free radical substitution, which is a wild chain reaction you kick off with UV light.
Let's look at that chain reaction, because it's pretty chaotic. First, a blast of UV light rips a chlorine molecule in half, creating two chlorine-free radicals. Now, a free radical is like a tiny, super-caffeinated, angry particle with an unpaired electron. It is desperate to react. So that radical violently smashes into an alkane and rips a hydrogen right off it. This turns the alkane into a radical, which then attacks another chlorine molecule, and the chain reaction just keeps going and going until, finally, two of these angry radicals bump into each other and cancel out. It's messy, it's uncontrolled, it's pure brute force chemistry.
Okay, now let's flip the script and look at the other side of the story, the alkenes. Their whole structure is completely different, and it makes them hungry for a reaction.
Alkenes follow a different blueprint. Their carbons use sp2 hybridization. So instead of mixing all four orbitals like an alkane, they only mix one s and two p orbitals. This gives them three strong bonds, but it leaves one p orbital on each carbon totally unchanged and available.
This sp2 arrangement makes the molecule flat, and those leftover p orbitals, they're just kind of sticking out, one above the plane and one below. They overlap side to side, and that forms a second, much weaker bond called a pi bond. You can think of it as this big, fluffy cloud of electrons just sitting there, exposed to the outside world.
And that is the whole secret. That's the key difference right there. Unlike the protected bonds of an alkane, this exposed, electron-rich pi bond is the alkene's functional group. It's basically a giant, flashing neon sign that says, "Hey, over here, come react with me," to any molecule that's attracted to electrons.
So what happens when a molecule takes that invitation? Let's watch the elegant step-by-step dance of a reaction called electrophilic addition. We'll use bromine as our example.
Okay, these curly arrows show us exactly where the action is. The alkene's pi bond, with all its electrons, is the attacker. It reaches out and attacks one of the bromine atoms, and in that instant, the bond holding the two bromine atoms together just snaps.
Now, this initial attack creates a really important but very short-lived middleman. It's called a carbocation, and it's just what it sounds like, a carbon atom that's now missing a bond, leaving it with a positive charge, and that makes it incredibly unstable and reactive.
So, what we have now is this temporary intermediate state. One of the carbons has formed a new bond with a bromine atom, but the other carbon from the double bond is left high and dry. That's our positively charged carbocation. And the other bromine atom? It took the electrons and is now a negative bromide ion.
And the story has a very quick, neat ending. Opposites attract, right? The negative bromide ion immediately sees that positive carbocation and boom, it swoops in, forms a new bond, and just like that, the reaction is done. The double bond is gone, and we have successfully added the two bromine atoms across where it used to be. Now, that all works perfectly for a nice symmetrical molecule. But what happens if the alkene is lopsided? All of a sudden, the bromine could add in two different ways, creating two different products. So why does the reaction almost always prefer to make one over the other? The answer, as it so often is in chemistry, comes down to stability. It turns out that not all carbocations are created equal. The reaction will always choose the path that forms the most stable carbocation along the way. And as you can see, a tertiary carbocation, one attached to three other carbon groups, is the most stable, followed by secondary, then primary.
And this predictable preference has a name. It's Markovnikov's rule. But it's not some kind of magic spell. It's just a really useful way of saying that a chemical reaction, if given a choice, will always take the easiest, lowest energy, most stable path it can find. The major product comes from the most stable intermediate. Simple as that.
Okay, let's bring this whole story home and put it all together.
And here it is, the entire story in one comparison. On the left, you've got the alkane's 3D fortress of protected, stable sp3 sigma bonds. It's built to last. And on the right, you have the alkene's flat, open sp2 framework with that big, vulnerable electron-rich pi bond just sitting there, completely exposed and ready for action.
So why does any of this matter? Because this one fundamental idea, that a molecule's shape dictates how it will react, is the absolute foundation of organic chemistry. When we understand this, we can predict what will happen. We can control reactions, we can design and build the complex molecules that become our medicines, our advanced materials, basically our entire modern world. It all starts right here, with the simple, elegant secret of the bond.